Okay, we're starting. I did do a test run with the new Camtasia Studio about a half an hour, 45 minutes ago, and I got it to work okay, so I'm hoping that it can process faster. That's what I always hope for. That's the big deal to me. Can it compress faster? So we're going down to the wire just to review the calendar here. Our final exam time slot, I haven't checked, but I'm virtually certain it will be on Thursday, and it's usually in the morning, and I think I actually pushed that up somewhere or another. I put it on some document recently. I don't remember which one it was, but I'm going to check that again. But if you guys want to check it for me to cross-check it, it's not so much that it's a conflict with our classroom that we go take an exam in, because that doesn't exist this go round, but it's conflict with other finals and such that you're taking. So I want to stick to that schedule because I want to make sure that it's sitting in the pocket where it belongs from a time perspective and not conflicting with other exams you might be taking. So I will be going through a review on Thursday. I have a review sheet that I'll be posting up. Actually, an old one is there, but I'll revamp it and think if I want to change anything on it. But the importance of it is I go through and I mark things on it, things that are of special interest to me in terms of the past material, then highlight what of the new material, and I have options there. It just depends on how things end up on Thursday. And this will help you in planning out your crib sheet. The exam will be of the same format as you just took last week. It'll just be a longer period of time, not extensively longer. And again, I will stick with the time allocation because there will be other exams that some of you may be taking, and I want to treat everything the way it would normally be done if it was on campus. So we'll be talking about the project, and right now I believe I have the project due at noon on Wednesday the 13th. We can discuss options on that. If that's not looking good, I'll have better feedback probably by Thursday as to how things are starting to pick up in the work on that, because it has a lot of pages, but the work that you have to do is not as extensive as you might think. And that's why I want to spend some time looking at it today as well. So I guess we will move over and look at the histograms. Really, because I haven't had the time to grade any homework, I haven't created any new scores in that area, and the quizzes are where they've been since before exam 1, so that histogram hasn't changed at all either. So I didn't push a new version of that up. If I do get some grading done, it just seems so difficult right now. I'm always pushing. I never get a chance to turn my engines around and pull back and grade because I'm always pushing out stuff. And right now I'm kind of negative on anything happening between now and Thursday because I'm handling questions from all 3 classes, but 2 classes in particular, questions on projects and finals, take-home final that's running in my phase lock loops class. So I know that it just keeps coming, and other things fly at me too that I don't even know what they're going to be. I get surprised is what it comes down to. I have capstone teams, but I've met with them yesterday, and I think the other team that I meet with is pretty good right now too. So this is how the exam scores shook out. I didn't have the mean that I could tell you last week, but it is 81.2, high of 93, low of 65, and not a large number of samples in the histogram because there's only 6 people active in the class right now. So what is significant though is when I take this data and now I merge that with exam 1 and then I combine that with the quiz scores, I can at least form a second histogram, which is called a pre-final average, which normally would have project 1 inside of it, and it also have essentially all the homework scores in here, which hasn't happened. It's like I said last time, it's my fault, but I'm spoiled because I've had graders in the past, and even though I have a small class, I still I spend about as much time preparing for class and managing the affairs of the class without grading. Grading takes time, lesser number, less time grading, but still it takes a lot of time just the same. And actually, my experience is when you have to grade just a few papers, you get no efficiency out of it because you have to ramp up on your efficiency by grading at least 10 papers, and then you start to hit a plateau of optimum speed. And when you're just coming up on new sets of problems all the time, you stay very inefficient. That's been my experience over the years. So what we've got on here is, I'm just going to write some notes down on here. We've got just 3 categories on here, so we've got 50%, if I'm adding correctly. 30% of the grade has been determined so far from exam 1 and exam 2. 20% will be determined by the homework and quizzes combined, and normally I've weighted those equally, so in this particular scenario, I may not do that. I may decide to put the quizzes at 0.4 and the homework at 0.6 of that 20% breakout. But right now, all I've got are numbers in there. And I haven't dropped the lowest quiz. I think probably I'm not sure what I'm going to do. I could actually decide not to drop the lowest quiz just to have the numbers in there, but then more heavily weight the homework grades once I have those combined together. You might vote otherwise, but I'll see what makes the most sense. So this is where we stand, though, and as I was saying last time, we have what we have sitting out there is we have the 0.3 or 0.25 from the final, and then we have 0.2 or 0.25 from projects. Projects 1 and 2. So that brings in the other 50% of the grade. And the way that I do this, just to review again, this is the nominal way that I do it, but if the project average is higher than what you do on the final, then I will count the project score grade category as 0.25 and drop the weight of the final to 0.25 rather than 0.3. So it's an optimization in my spreadsheet. I choose whichever of those 2 options gives you the best overall score. And you can see what the distribution is. It's kind of, it's not exactly what I'd call ideal. We've got 2 down in the 60s. We've got a clustering in 70 and 80s area, upper 70, low 80s, and then we've got 1 at 91.1. So there's 2 big holes in the middle there, and it'd be nice if things were spread better. I mean, if you were a blind person who didn't have corrected vision, let's say you'd look at this and you'd say 3 blurry blobs, I'll give 3 grades, and they could be C, B, and A, or they could be, C, They could be D, C, and A, or whatever. I mean, and I'm not saying that's what I'm going to do, but when you have a giant separation like that, it kind of looks like that's the natural clustering of things. But that's not what I'm planning on doing, and honestly, I don't expect it to turn out this way. I expect there to be some more centralizing of these values is what I tend to think is going to happen. I think some things are going to shift up all the way across the board, and they're probably going to get the histogram bars are going to get closer together is what I think. So I can speculate right now, but it's not something that I want you to. If I say it, it's not something that I want you to get worked up about, because a lot could happen when you've got that much 50% of the grade sitting out there. And you can do the math yourself if you decide to direct channel message me and say, so where am I at on your spreadsheet right now? And I can send that to you, and then you can play the game where you say, okay, I've got this number in this box, and that is going to be weighted on the rework of this as 0.5, or maybe even break it out separately. You can just say, I've got a couple of numbers out there, and then you can play around with those numbers. Just break it up into all these categories if you wanted to. I don't really want to spend a lot of time on this because I've got definitely important things to talk about, but this would be 0.3, that would be your exam average right there, and then you could go times 0.2, and that's going to be split between the quizzes, which are already determined, so I can give you that number, and then you can guesstimate where you're going to land on the homeworks percentage-wise, and then this would be the 0.2 for the projects, the 2 projects that are in there, and then the final at 0.3, and then you could rework it if you wanted to and switch the last two around to say they're 0.25 and 0.25 each. But this is all known, this is partially known, and so you could put numbers in the unknowns and just see what sorts of things would get you in a certain location. And my plan is to be able to work within that type of scenario, but I do bending if I have to. So this would nominally be A, B, and C, and then at the edges I would have the plus and minus grades. But as it would stand right now, if I had to give grades right now, I would not be able to give but one A, but I would probably give B's to both of those, and I probably would give a C plus to this one. And down here, I don't know what I would do. It should be a D, but could it be a C minus? I hope those numbers don't stay there, is all I can say. I hope that changes. But I do what I have to do, and I can't tell you that ahead of time because I don't know what the numbers are going to be. It's something that you don't really know until you see it. And I'm hoping that things are going to look more enticing when that time comes. And that will be when I'm all alone grading papers, probably the week after next, when I'm still finishing on Sunday and Monday at the week after next. So I'm also a person that gets behind and I stay behind. So if I look at the calendar, it will be in this time frame, the 18th, and if I have to use the 19th, it just depends on how many things keep flying at me. The administration has me at a budget committee meeting on Thursday, so I definitely probably have to be done by the 19th. They're probably going to tell me the grades have to be in by 11 p.m. on the 19th. So, does anybody have any questions or comments that they want to make right now? And if you don't want to, that's fine. If you want to message me, a personal request or something, that's fine too. I just thought I'd go through this, and I generally go through this on the very last day, but I generally have the hard press on a grader or something to get everything back to me except for the last homework assignment and then the last project. And that's not going to happen with me. I know that right now. I'm not going to be able to, I might be able to do something, but I don't know what I'll go for first. Maybe if I get any time, I should go for project number 1, since that's worth quite a bit. So what's left on here then is going through the exam questions themselves, and unless somebody has a specific request, and I guess what I'd like to do on the exam is have you study my solution, and if there's something that's really bugging you, you could direct message me and we'll deal it out there. But if it's something that's more universal that you think the whole class would benefit from, bring it up during the final review on Thursday. So another student is hacking me for a zip file that's not correct. That's the normal stuff with me, though. I'm working late at night and always under pressure. Pressure is the name of the game. So I'm going to take time out and just respond back to him from Phase Lock Loops, I guess it is. You guys never got to see Rosanna Dana. That was her famous saying, always something. And that's what I feel like all the time, especially at the end of a semester. Okay, so nobody's saying anything, but do that, and that way we can move forward with the material. And I certainly will be looking at this to see what in memory were things that were problems, and those are the types of things that I will be more likely to revisit on the final exam since it's comprehensive. But I reserve the right to say, okay, everybody did fine on this, everybody did fine on this. I don't intend to retest on that, but if it's something that I was not really happy with, I will make a point to let you know that I'm going to be testing on that again in the comprehensive. So it's very quiet right now. I have no idea if anybody's actually listening, but I'm assuming so. So what I want to do, we're going to get into the system side of the physical noise sources, and we're going to see how it's a straightforward procedure to do these problems, but it's very vital in link budgets, in comm systems, to understand how noise enters in. But we're going to leave the circuit world, but I want to at least spend a bit of time on it and go back momentarily and visit Nyquist's formula. We started with simple resistor circuit ideas, and it came down to this simple model, 4KTRB. So it's really KTB noise, or thermal noise, is what we'll be getting at, because we're going to be getting the impedance R to actually leave the equations when we're doing maximum power transfer. Don't see that just yet, but we'll get it down to that point. But for this circuit right here, before we had Nyquist's formula, we had to superimpose all the noise sources. And there's likely, there will be at least one problem on the final that will involve this type of calculation. But with Nyquist's formula, it says, no, we don't have to do that. We can just get the impedance looking into the circuit. And once we have that impedance, in particular if it's a purely resistor network, then the noise is just 4K TR equivalent times the bandwidth B. So that's a really nice result. So I have an example here that I worked out in a circuit simulator, And rather than show you the circuit simulator results here, I have LT-Spice running, so I'm going to go over and bring the circuit up over there. But in this particular circuit, we've got 4 resistors, and according to Nyquist's formula, the equivalent resistance looking into that network is the 100K will be, which is right here, is going to be in parallel with the 3 resistors that are in series. So that calculation is right here, 100K times the series connection of 10, 5, and 20K. Put those up in parallel and you get 25.93K. And then Nyquist's formula says that the noise voltage squared is 4kT times normalized by the bandwidth. So in this case, we don't put bandwidth in the expression. We divide through it on the opposite side, and then we take the square root of both sides. So we're going to get an expression that's VRMS per square root of hertz. And this is commonly used in circuit modeling, where you want to look at thermal noise effects in a low noise circuit. So yes, we did have 4kTB times R equivalent, but what we're doing now, and that's equaling V squared, so what we're doing though, pen just kind of stopped on me, we're taking the V squared over B, which is in hertz, and then we're taking the square root of that and setting that equal to the square root of 4kT R equivalent. And that's the way circuit analysis programs give you their results. So if we do that for this circuit, have it normalized in that fashion, we have 2.072 times 10 to the minus 8 RMS volts per square root of hertz. And then you apply the bandwidth, or let the network apply the bandwidth by itself through the filtering action of parasitic elements and so on. So here is a circuit that matches what we just have in that model over there. So what I'm going to do here is I added a capacitor just because that's the next example I have in the notes. I'm going to go in here with the scissors and disconnect that capacitor. And in the circuit modeling, you have to put in a voltage source just as a dummy source, and I just set it up in AC 1 at an angle 0, but I'm doing noise modeling here. So it's the dot noise command, and I'm saying give me a sweep in 100 points per decade, starting at 10 hertz going up to 1 megahertz. So if I hit the running man over there, I get my plot, and if I go and hit this and then move the cursor somewhere around, it's already here, but I'm getting exactly what our calculation is. We're getting 20.72 nanovolts per square root of hertz. So that's exactly follows the modeling over here. So it's just letting SPICE do it. But the cool thing about this, Nyquist's formula said it involves the real part of the impedance, so we can let SPICE take care of that. If I have a reactive element in here, I can just go ahead and rerun this circuit. And now we're going to see the effect of having this capacitor in here is that it changes the shape of the noise. And really what's going on here is that when you're at a low frequency, the capacitor looks like an open circuit because capacitive reactance is 1 over omega C, right? It's negative reactance, but so it looks like a very high impedance at a low frequency. So it looks like all 3 resistors in this series branch are active and then in parallel with a 100K. But then as the frequency goes up higher and higher, we're rolling off down here into this zone, and that's because the capacitor now is acting like a short circuit and it's shunting it's shorting out the noise that's being generated by that 5K ohm resistor, so that reduces the noise level down. And we could theoretically go after that. I haven't done that here, but you could, move the cursor over into here and just verify that that floor is what you'd get if you take the 5K resistor out of the circuit. And of course, if you want to do other things in SPICE with active components and things that have different types of noise generation mechanisms, then SPICE will take care of all that for you too. I'm showing this to you because you may bump into this someday. I had never used it, but then I worked on a problem for a company called NavSys, and I helped them with a frequency synthesizer that was having some noise issues, and I ended up modeling everything in SPICE so that I could understand where the noise was coming from. So here's the rest of the modeling that I had done in that problem, and I did go through the circuit model and got the shaping effect just from circuit analysis. And when I did the work at NavSys in their RF frequency synthesizer, I ended up digging out a model for a noisy op-amp, which has noise sources, 2 current sources and a series voltage source. This is a standard op-amp model, and then you go to the data sheet for an op-amp, and it gives you for a particular op-amp what the noise voltages and noise currents are, so you can include that in a circuit model. And a few other things that are out there. This book that I referenced down here is an old-timers book, but it was freely available on TI's, I think it's still freely available on TI's website, and it was kind of helpful because I used that in developing my behavior level model for the synthesizer loop filter. It was for the loop filter component. Active devices, diodes, and transistors have shot noise, which is due to the discrete nature of current flow and electron devices. I'm not going to spend any time on that because there's not any questions on it, and it's not the primary focus of this appendix, but it does overlap with parts of your background since you do take some semiconductor device courses along the way, and shot noise perhaps is talked about in there. I never thought I'd bump into shot noise, but when I was first in industry, I worked on a laser communications system. This was after I'd gotten my master's, and the optical comm link has got additive noise due to the receiver electronics, but there's shot noise associated with the photo detection process, and that was certainly a factor, and I studied that when I was doing my master's thesis. So I have been in that domain at least once in my life where I had to think about shot noise effects. And then these are just some other types of noise sources that you can model that you would bump into in certain scenarios. So now we're going to jump into the systems modeling domain, and we're going to first establish the idea of available power, and then we're going to start looking at, the next topic after this will be noise figure. So we're going to look at how when you have a cascade of subsystems, we will have some noise at the front end due to an equivalent resistance, like the resistance of an antenna. We'll have a noise temperature sitting out here, which is due to where the antenna is staring up into the sky, perhaps picking up a bright star or the sun. But then we'll have the idea of every subsystem has got some injection of noise associated with it. So we have an input and an output, input and output. So we have SNR changes as we go along a signal processing chain. And I'm trying to think. It's been a long time since those of you who were taking the lab have been in the lab, but the spectrum analyzer has a noise floor associated with it, and the spectrum analyzers we have in the lab, the Field Foxes, have have a nice add-on feature that I explicitly specified when we bought them, and that is a low noise preamp, so that if you're using the analyzer with an antenna and you want to capture some weak signals, like I was going to have you do in the final lab of the semester, you could turn on the low noise preamp, and then the noise floor drops because you have a much better noise figure associated with the front end of the actual spectrum analyzer, which is like a receiver, and that would allow you to see a weak signal above the noise floor that you might have if you didn't have that low noise preamp. Just a curiosity thing. You may have noticed that preamp was an option, though, in one of the menus. You could turn it on and off. So at any rate, to get to that domain, though, we first have to just review through how RF circuits are generally configured. So an RF circuit is something that involves transmission line theory. But at the circuit level, it starts off by saying that you've got a source, and it's got a source resistance, and then you've got a load at the other end that has the load resistance. So collapsing that all down to a simple circuit model, we'll have something like a source resistance R. This is typically 50 ohms in most RF environments, but if it's cable TV, it's 75 ohms. And then at the receiving end of the system, you've got a load resistor, and generally you have that matched for maximum power transfer, something you learn about in circuits. So generally this is 50 ohms. And if you were doing a current source, you would have the admittance, and the real admittance would be G, which is 1 over R, and the load admittance would also be G. So that's why I've said maximum power transfer is implemented, and that just is common sense. To want to have maximum power transfer, we don't want to have reflections on the line, standing waves, things that are bad form for communications systems where we want to get an efficient process going. We don't want to lose things. We want to get things from one end to the other. So maximum power transfer, if you look at the circuit model up above, you'd say the power available is the power that's delivered to the load through maximum power transfer. So we go through by saying different ways of looking at this, but the typical way I would look at it would be that it's going to be, pencil just quit again. The voltage at the load under the maximum power transfer is when we have the matched resistance R to match to the source resistance R. So we're going to get VRMS is going to get divided in half as it arrives at the load, and then we square that value, and since it's an RMS value already, that is going to be the correct term to be using in a power calculation, as in V squared RMS over resistance R of the load. The 1/2 is sitting in there just simply because of the transfer from a source at 50 ohms, let's say, and a load at 50 ohms. So that reduces down to this kind of standard result, which again, those being in the lab saw that some of these calculations in the very beginning when you were learning how to use a spectrum analyzer. So the source open circuit voltage, V squared RMS over 4 times R, is what we have. So if we had V squared RMS coming from a noisy resistor, that was the 4K TRB value that we were dealing with earlier. So then we're saying if we had a noisy resistor and we were delivering its voltage that it produces to a load with maximum power transfer, what happens here, and this is pretty convenient actually, the R values go away and we get KTB times KTB watts is what we're going to get. So this ends up being our thermal noise calculation. R drops out of the equation, and this is the W there is for watts. So it's just sometimes called KTB noise. And if we consider room temperature as being around 290 degrees Kelvin, then we can go through the calculation that we just did, and we can divide through by bandwidth in that expression, and we're going to get a constant K times T naught, which is 4.002 times 10 to the minus 21 watts per hertz. That number is kind of obscure to me in my memory banks because I was taught something a long time ago when I had comm systems. And before we actually get to the blue boxes at the bottom of this page, I just want to quickly review how power ratios are calculated using 10 log base 10. When you're in electronics, you generally do 20 log base 10 because you're talking about voltage ratios. But since we're already talking about power, we don't have that squared that brings the 2 outside of the logarithm to change 10 to 20. So we have a power ratio, and 1 watt is referred to in dB as 0 dBW. So that's 0 dB relative to 1 watt is 0 dBW. And then we have the other unit, the milliwatt, which is power reference to 1 milliwatt. So 0 dBm corresponds to a power of 1 milliwatt being delivered to a load. So if we take both of those definitions into account, and then we jump over to the power at room temperature, the power density, then we get these two famous numbers. And to me, this is the number that I was told when I had comm systems. Remember that number, minus 174 dBm per hertz is the thermal noise floor at room temperature across when driving a matched load. That would not be a resistor that has excess noise. It would just be the thermal noise floor. And that's created through the analysis we have right here at room temperature. The R's cancel out, so it's just K T0, which is the 290 Kelvin, and so on. There is a frequency dependence actually associated with this density, and that has to do with quantum effects. We have Planck's constant, and then we have this exponential, and then we have this roll-off that occurs. But the thing is, the roll-off is at a very, very high frequency. So if we're at 290 degrees Kelvin, we're way up in here where that would occur, and that is still a very, very high frequency. That's like 4,000 gigahertz. So for all practical purposes, the noise spectrum is constant. So in the regions of interest, even if we go down to a colder temperature, it's still pretty flat. At a very cold temperature, it's no longer flat, but at room temperature, it definitely holds up, and that's the minus 174 dBm per hertz is what we're talking about. So that's where the term white noise comes from too. When we say a device is producing white noise, it's because the frequency band of interest is low enough, and that doesn't have to be that low in frequency to make it look like a constant or flat noise spectrum. The quantum noise is the HF term that would raise it back up again as we go up very high frequencies. But as this bullet here says, thermal noise dominates. We now are operating in 5G in millimeter wave systems, so things start to change up there, and I haven't done calculations up there with noise, but that goes up above 20 gigahertz in the 5G systems that are being utilized now. Any questions? I'm going to move into the next level of system modeling. So now we're going to go looking at subsystems, an array of subsystems, and this is kind of what fades us back out of Appendix A. So the first thing is, like I've already started to talk about, it's a cascade of systems, It might be a preamp at the front end. It might be some transmission line between the preamp and the next subsystem, and that's pretty common in a or in a dish network setup where you have a preamp right out at the dish that's pointing up to the satellite. And then you have feed line, which is another subsystem to go from the back of the dish into the house. And other such components, mixers, amplifiers, and things. Those are all the subsystems and filters that you would have in a cascade analysis. So what we're interested in as a starting point is what is the noise figure of a system. And it's a measure of the noisiness of a system for starters, and the notation that Appendix A uses, it just says pull one of these subsystems out, call it the L subsystem, and we're going to assume that there's an equivalent temperature associated with the noise source that's driving into the input of that subsystem. If it's like a 50 ohm coax, that is going to be 50 ohms, and then we have the equivalent temperature associated with that source. So the noise figure is defined as the signal to noise ratio at the output and it's said to be equal to 1 over the noise figure of the input. And one of the things that's true about noise figures is they're always greater than 1. And it's a measure of how noisy the system is. So the noisier the system is, the bigger the number F sub L will be. It will exceed 1 by some amount. And what it's saying is the signal to noise ratio drops as you go through a subsystem, a real physical subsystem. There's no way that you can come out ahead in going through a subsystem. You're always going to have some reduction in signal to noise ratio due to the noisiness of the subsystem. And it's just an indication that, as this says, each subsystem generates some noise of its own. We work most of the time with in specs of subsystem components as in terms of the noise figure in dB, and the relationship between the noise figure and the noise figure in dB is just 10 log base 10. Generally, though, when we're doing the calculations that we're going to talk about, we have to convert back from a noise figure in dB as the spec for a component and get it back to the ratio side over here. So we're going to frequently be doing things like F sub 10 to the F in dB divided by 10 to get back to the ratio FL. Moving along a little bit further, we can assume maximum power transfer again, so available signal power and available noise power are the terms that get used. And if we go through that analysis, then the available noise power at the input side is going to be KTB, just like we've been talking about when the impedances are matched, or maximum power transfer. So it's Boltzmann's constant times the temperature in Kelvin effective of the source, TS, temperature of the source, times the bandwidth. And then if we assume that the L subsystem has a power gain of G sub A, it might be a 10 dB gain preamp or something, then we're considering what is the power from available at the output of that L subsystem. So that's the power from the source that's available. That's what the SA is at the output of the L subsystem, and that will be the input noise power times the gain. And what we're after here is how noise figure enters into this expression. So if we go through this analysis, we'll see that noise figure pops out directly from the definition. So that's how the noise figure is going to be reduced. And if we actually go into the modeling then to solve it in terms of the available noise power at the input and the available noise power at the output, we end up with this definition that says ultimately, I mean, along the way, it's this result right here. But what we're really after is the noise figure. So this is just an algebraic manipulation. We have this assumption, and that's assuming that the noise power at the output is the input noise power gained by the gain of the device plus the noise that that system is adding. That's just the reasonable assumption. If it was a perfect system, there would be no internal noise, but we're just saying the fact that it is internally generated noise. So the noise figure will then come out to be 1 plus the internally generated noise divided by the gain K, TS, and B. And that leads to the next blue boxed equation, just saying that that is how noise figure is measured. And generally when you're speccing a device to sell to somebody, you will specify that to be room temperature so that you're not specifying it as some relative to some other source temperature. Now, when I was in school, I distinctly remember my professor that taught me this stuff said, you could be a deceptive salesperson and you could sell devices where they would use TS other than T naught. And so they might use a TS that's hotter than room temperature, and then that would drive down the noise figure for that device. So you could be selling amplifiers that had really low noise figures, but it would be deceptive because you would only realize that low noise figure if you operated it in an environment that was running really hot. Whereas the correct way to specify things is at room temperature. So when you read a data sheet, you should expect to see, when you see the noise figure for the amplifier you're buying, you should see them talking about it being at room temperature. There's also techniques that you go about for measuring noise figure, and I'm going to skip over this area. It's interesting. I'm pretty sure the technology has changed. When I was in industry down in Arizona in particular, we had a noise figure test set that we would use to measure the noise figure of subsystems that we would either buy or build. And I can see a typo in here. Should be device. And a project that I was on, I had to build a low noise preamp. This was the interface to a photomultiplier tube and the front end of the optical comm system that I was responsible for on my very first assignment. And so I got exposed to that. After I built my preamp, I had to go get checked out to me the noise figure test set from the test lab. And then I had to do measurements on it and see how it was looking. And later, way down the road from there, when the customer was there to buy all the equipment, I had to, again, get that equipment in the lab with the calibration stickers updated on it so that I could run through the test for the customer to say, yes, your low noise preamp is meeting your requirement. I don't remember what the number was, but it wasn't a hard thing to meet. And I wasn't an expert at building low noise amplifiers. I just followed some examples that other previous generation of the system had used and bought some kind of expensive microwave transistors and designed a PCB, and it got put inside a little tiny aluminum machined housing, and that was the preamp. And it sat remote from the rest of the electronics. It sat right at the back end of the photomultiplier tube. Kind of like my analogy to Dish Network, where you'd have a preamp right at the back of the antenna on the side of your house. So these are just a couple of measurement techniques, but I'm skipping over those. There may be homework examples of this, but I'm not that interested in it. Does anybody have any questions on those things, though, or see themselves doing that at some point in the future? Being involved with low noise and testing components out and things.
I'm sure it's a possibility at some point in time.
Yeah, I think the reality is, I mean, you don't know where you're going to go with your career, and as things happened, that's one of the things I'm struggling with in my mind. How those of you that are seniors are going to start your first jobs, because when I started my job, even though I had my master's degree, because I did that straight away, I had a mentor, and I had, as far as I'm concerned, I had more than one mentor. I had an official mentor who was assigned to me, but then I had the members of my team that were all more senior engineers, and I had to ask everybody questions because I didn't know about any of this stuff, and it was somewhat terrifying for me because I worked at a plant, and I've told the story before, that had 4,000 people walk in the doors around from the big parking lot down in Scottsdale, Arizona. I still can't imagine that. That's 4,000 people going into one building is a lot. And the hallways, it was just a huge building, and it had everything in it in aerospace electronics. Torpedoes over here, satellite stuff over here. I mean, secure communications was buried in the basement, and there was no way you could get close to that. But I always liked the walking past where the torpedoes were getting put together, because that was real mechanical stuff. There were these long stands that they were mounted on in the production area, and it was interesting. Never done anything with naval type electronic systems. So we're going to move on to now is a little interlude, resistors in series and parallel, and this is just going to lead up to an analysis. Well, actually, I'm going to skip over this one. This one is not really all that relevant either. This is just modeling components again at different noise temperatures. I'm going to skip that, though, because that's not super interesting to me, but this next one is effective noise temperature. This one we will be using. So we have the noise figure at a stage, and was 1 plus the internal noise divided by the gain, and then the noise temperature that the input was referenced to. So we have this expression. And in reality, that is equivalent to saying it's 1 plus the effective temperature of the device, the L stage, and room temperature. So if we actually break this out of here, we have that part of the calculation. And the curious thing is that does have units of temperature. If we go back to the formulation with Boltzmann's constant and everything, that this will have, this quantity right here does have the units of temperature. So that becomes what's known as the effective temperature, which is a measurement of the noisiness of a system in terms of temperature. And the idea is that the hotter the temperature is, the higher the temperature is, the more noisy the system is, and the lower the temperature is, the quieter the system is from a noise point of view. So we can go back and use that definition and establish through that definition what the noise power available at the output of the L system is. And it starts with this part of the calculation. It's the gain of the input times, it's the gain of the subsystem times the input noise power available plus the internal noise. And then if we write what that internal noise is, we can write that from our expression up above here is K times T effective times B, and then the real important thing is what you get right here. This is probably the most important equation that comes out in this section right here, is that the power available at the output of the L subsystem is the gain of that L subsystem times Boltzmann's constant, and then times the quantity, the temperature of the source, plus the effective temperature of the component. So this is just another way of modeling in terms of temperatures, and this ends up being used an awful lot. It's a way of modeling an entire subsystem lumped together, and I guess what I'm going to get at here, we're going to see an example of this, but suppose this is your antenna, and it's looking into the sky, and it sees an effective temperature T sub S. It might be hot, it might be cold, and then we have sitting over here our entire chain, our cascade chain, and we just have it all lumped up to say that it has an effective temperature of so many degrees Kelvin. So then we're interested in, we'll be interested down here in what is the noise power available at the output of our entire system. And then that will be compared to the signal power that we're getting based on the antenna's gain and how much power is being radiated in the distance and all that propagation stuff. But it's the TS and the TE that come together through this equation I've outlined in red to figure out what the noise power available is right at the output of the system, which might be at a certain detector point inside the receiver where you're interested in doing a calibrated measurement. I don't know if that's interesting or not, but I've certainly had people in this class before that have talked about how noise temperature of the source has been a factor. They've been out in the Middle East or something where they were trying to point to a satellite, and the alignment of the satellite and the sun were coincident just for a short period of time, and they couldn't receive their satellite signal because the temperature of the source was just way too hot because the antenna was pointing right at the sun, and the satellite was right in that line of sight. I mean, it was not on the other side of the sun, obviously, but it was in front of the sun, and it was just too noisy when they had the antenna pointed straight towards the sun. Is that believable? No one wants to refute that, but I've had people over the years that have testified to that their commander was unhappy. They said, our link is down. Why is your link down? Oh, we're pointing at the sun right now. We can't get enough signal power to come up over the noise of the sun. So we're going to move on now to the cascade, and I may save this for next time. I'm trying to decide if I want to jump over to the project for a little bit and then do the wrap up on this part. This part moves along pretty quickly with Free's formula, and then we go through some examples, and this is exactly what the quiz has in it. It has an example like this, and then the very last thing is free space propagation, and then there's an example of this as well. So it's actually looking at a link that you would set up between a satellite and a ground station, and it talks about modeling with omni antennas and antennas that are aperture type that have gain over isotropic, and that forms the whole link budget equation. And this is pretty straightforward stuff. It's just adding and subtracting if you're doing things in decibels. So does anybody want to chime in, say keep going on this for a little bit, or talk more about the project?
Project.
Okay. Was that you, John? Or no? I didn't.
No, that was Will.
Okay. I wasn't sure because your voices are a little bit similar. So, okay, I'm going to go over to the project then. And I've got it running in the Jupyter Notebook right now, so we'll be able to look at that. So like I said before, the project has got a lot of writing in it, but if you get down to the core tasks that you're going to do, there's not really that much, and it's just a matter of doing measurements. But as Chris found out today, you have to be careful because he made some mistake, which I don't fully understand, but we're going to talk about that when the lecture is over with. And that kept him from getting things to work out nicely. So I have to get in here to the section where the questions are. We have part 1 and part 2. Right now I'm drawing a blank because I don't remember are all the questions for part 1 lumped up with part 1? Those of you that have studied it, because I'm forgetting since I've been working so hard on my phase lock loops.
They're all together at the end.
Okay, that's what I was thinking. The project that
Yeah.
right.
Everything listed at the
Okay,
end.
well the thing I've been working on for so long and so hard for phase lock loops is distributed. So it's some discussion and then some problems. So the first few questions, which are 1, 2, and 3, pertain to the first half. And the first half is a model where we're looking at quantization, noise effects, and the very, very first thing is just studying the need for scaling, which is a 2's complement overflow issue. And then after you get that resolved by figuring out how to scale properly, then you go ahead and take a series of measurements where you're going to set the quantization level differently for each, to represent a different number of bits. So you're going to define in the PCM encoder and decoder different numbers of bits. So you're going to start at 4 bits, and then you're going to go up to 16 bits. And you're going to get an output signal to quantization noise ratio that just linearly steps as you increase the number of bits. As you go from 4 to 5 to 6 to 7 to 8, it'll just change by 3 dB per bit, I think is the number. And when you collect the data, you get just a perfect, really nice straight curve. I mean, straight line. It's just sloping upwards. And if you listen to compact digital audio, you're listening to encoding with 16 bits. And if you're listening to telephony, it's about 7 bits on the cellular network, on the telephone network. So you start that process with A, and then the next thing you do is you do an experiment where you're going to play one of the speech vectors through, and you're going to change the number of bits to see how low you can go and still have it be intelligible. And then, so that's 1, 2, and then 3 is just playing around with coding. So you're going to put some coding in the system, and you're going to get the impact of additive noise in the channel now producing bit errors in addition to what the quantization noise is doing. So I'm going to jump over and look at the Jupyter notebook that goes with this. And this is what I call the Project 2 sample. So I think, I just loaded this, so I have to run some cells here. And to do the things we want to do, we need the digital comm module, which has the PCM encoder and decoder in it. And then to do problem 3, we need the error correcting module. So let me just jump back over here since I want to talk a little bit about the reading. So the questions seem a little bit obscure, but what you have to do is you have to go look up into the reading to see some examples, typically, where I've even run some results out. So the mean squared error idea is how we're characterizing the difference between an encoded, between a decoded analog signal and the unencoded and decoded signal, so one that doesn't have quantization error. And I'm trying to remember, do I have any pictures of that? If not, I'll run those pictures. I'll run an example though of something. So what you're doing initially is you're going to take an analog message, encode it. You're not going to use the Viterbi or the forward error correction initially. You're just going to take it out and run it straight through your channel, which eventually will add additive noise to it, as if to say it's being received at a receiver at a low signal to noise ratio. And then that comes around and initially bypasses the Viterbi algorithm for decoding, but just goes straight into the PCM decoder, and then you get to listen to it again. So this M hat is close to M, but it's due to the effect of the quantization that you get some impairment. But then when the noise level becomes higher, the received signal to noise ratio is modified, as if to say the signal is going through a poor channel, then some additional bit errors occur. So let's take a look at that. I'm also importing from SciPy Stats, although I don't necessarily think you have to use it. I'm trying to remember whether it's used or not. If you've been taking Province Stats, though, you might have been using SciPy.stats, or you might be just using the stats functions that are in NumPy itself. I kind of introduce those guys right in here. Let's just take an example. So here I've got a 75 hertz signal that I'm generating. And here I'm importing the British male voice that we've used before. And of course we've listened to that voice before.
The little tales they tell are false.
But what I want to do down here is not use that voice initially. I just want to use the sinusoid. So I'm going to change this to M. So I'm going to rerun this. If I run this cell, I have M. If I run this cell immediately, I'll replace it by the speech. But I just want to do a test with M. So I just want you to verify initially, the very first task is the need for scaling. And one of the things to remember about learning in digital logic or logic circuits or somewhere, microcontrollers, I'm not sure where, is that when you have 2's complement arithmetic, say you have B bits, the first level of quantization sits at -1 if you have everything normalized to a -1 +1 system, and then the highest level you can go to is 1 minus 1 over 2 to the NB minus 1. So what I'm thinking of right here is something that you're familiar with from your computer arithmetic. If you have a 16-bit signed integer, the largest negative number you can go to is minus this, minus 32,768. But then the largest positive number is 2 to the 15th minus 1, which is 32,767. So you've got to be careful to make sure that you actually, if you've got a symmetrical signal, you want to make sure that you don't exceed 32,767. So here I'm putting in that scale factor to make sure that happens. I'm going to be PCM encoding M, which was the sinusoid, and then I send it through my channel as bits, data bits, and then I decode it. I'm setting this channel signal to noise ratio very high, so there's essentially no additive noise in the channel. And then I get my decoded bits back out as D hat, and as D hat, and then I send them into the PCM decoder and get M hat back. So let's just take a look at that. Here I'm just plotting visually what you've got, and this is for a very small bit level, I'm only putting in, 3 bits. So it's pretty obvious that you have quantization error. If I didn't use scaling, what would happen in this case? Suppose I take the scaling out of here, and I see up here that it's just a cosine that swings between plus and minus 1. So if I don't scale it to avoid it from overflowing, and then I go through this cell right here, I have something really bad happen. When the positive peak of the sine wave exceeds that 1 minus this level, 1 minus 1 over 2 to the NB minus 1, I've exceeded the maximum level I can represent with my quantizer, and 2's complement rolls. So we get it rolling to the most negative value at that point because of the overflow. So we want to make sure that you have the scale factor in here, and that's just because of the overflow that occur. And of course, that overflow gets less and less of an issue as the number of bits goes up. So let me just put that back in. And then I'm going to increase scale to about 8 bits. And then if I go ahead and compare at this point, they look pretty much the same. You can see a tiny little difference. In actuality, if I wanted to compare these properly, I need to put scale on here because the input should be scaled to apples and apples compare it. And I think that might be where you made your mistake, Chris. I'm not positive. But in order to get the minimum, in order to get the squared error between the input and the output, you need to compare them on an apples to apples basis. So I encourage you to get the mean squared error, which is the sum of the squares of the differences, just using the variance statistics function, because that will give you what you want. It will give you the mean squared value. So if you took m hat coming out, and then subtract that from m scale, just to make it apples to apples comparison, I get a number like that, which is what I'm hoping for. This is the mean squared error, the sum of the squares of the difference between the input that's been scaled to match the scaling that goes into the encoder and the output. But now because of the quantization effect, we're getting a small amount of error, and that's a measure of the quantization error, and 1 over that is the effective signal to noise ratio that gets talked about over here, way down here in the problem statement itself. If I can find it again. Yeah, so 10 log base 10 of 1 over MSE, so that would be calculated at the end. So you'd be doing something like 10 times log 10 of 1 over that. So 52 dB of signal to quantization noise ratio. You're going to be doing calculations like this using the speech vector in the very beginning. Isn't that right, Chris? It's using the speech as opposed to the sinusoid.
Yeah, I use a sinusoid to work with before I do speech stuff, though.
Well, you want to practice with something that's simple, is what I was doing.
Exactly.
So there's
I have the same thing.
okay, there's something else I want to point out, though, that's going to be a gotcha, and it usually happens, and that is because this encoder and decoder has to take samples through in such a way that it's a multiple of NB bits, there's going to come a time when you're increasing this number up from 8, 9, 10 all the way up to 16, that the lengths of m hat and the length of m might be different, just because you had to have an integer number of samples. And so how do you fix that problem is you have to recognize the fact that down in here M is not always going to be the length of, M is going to be larger at times than M hat, so you just need to make sure this goes up to length of M hat or something like that. See what I'm doing there? I'm just making sure that the lengths are equal. Otherwise you'll get an error saying that NumPy can't do a vector or an array operation because the lengths must be the same. So this just makes sure that the one that's always going to be longer, if possibly, is M, because the output might get trimmed slightly. So I'm just tweaking it to make it match. And it looks like I may have messed up on a parenthesis here. No, I guess I'm good. Yeah, my parentheses are still good. So that doesn't change anything here, but it might be an issue at a different value. So when you get into problem 3, now you're going to be looking at the effects of the full system, where you're inducing errors through additive noise. So here you've left the signal to noise ratio high, so you don't have any bit errors due to the radio channel or your simulated radio channel, but down here now you're going to change that, and you're going to actually be doing a listening test at the end, where you're going to set the channel signal to noise ratio down to 6 dB with the speech, and then you're going to process it. It will be kind of slow, but you're going to use a configuration that I define in here on the Viterbi encoder and decoder. And the main point of this, and I'm way out of time for sure, is this is kind of the big deal that comes out of this. There's a lot of discussion about how the Viterbi algorithm or how convolutional coding works, but I just want to get back to the block diagram and then make some comments about that. You're going to be using a rate 1/2 code, which means you're going to protect the bits that come in here with a rate 1/2 code. That means every bit that comes in here, you send 2 bits out in the channel. And those 2 bits go through the channel. They're subjected to a pretty harsh environment with the noise level being really high. But then the Viterbi decoder can decode that back to the original bits, and you get a very large amount of processing gain with the Viterbi decoder. So much so that even though you've had to send twice as many bits per second through the system, because that's the downside of forward error correction, is you're going to be sending more bits per second, which will occupy more bandwidth, but you end up making the system more subject to noise, because now you have less energy per bit when you increase the bit rate in order to accommodate the encoding. But the convolutional code that's used here is so powerful that it gets you back all of that and then some. So the main point will be to listen to it with the 6 dB channel to EB over N naught or SNR in the channel, so a very poor quality channel, versus one that's not protected, and it'll be an amazing difference. It's striking. It just shows you the power of forward error correction, and that is used in our comm systems today. More powerful codes than this are used, but this one is modeled with the module I have for forward error correction, and I originally wrote it for rate 1/2, and then Jared's brother Andrew helped me modify it to do rate 1/3 forward error correction coding. He did this for an independent study on open source software engineering so that it could be added to my package. So it's pretty cool. So I just want you to see the impact that coding has on our lives by actually sending it on through. Initially, though, it starts with just the quantization, with assuming the bits get through the channel without error, but then you start increasing or decreasing the signal to noise ratio, and I think I demoed that to you last time. Let's just see what it sounds like right now. We could very easily do it. We can just set let's see. If I went down in here to this, I think it's set up that I can do that with the tone. SNR is 8. I'm setting it at 16 bits. So I can send the non-speech through here directly, I believe. How do I want to do this? If I want to take this out of here, I want to keep the scaling in there, but PCM encode, yeah, PCM encode, PCM decode, yeah, this will be the uncoded system. And if we go ahead and listen to this, well, I'm not getting anything, so let's see if I did this right. I guess I just didn't have a long enough message, probably. Has anybody started playing with this yet?
Yep.
How long did you make it? You have to make N a lot bigger than 20,000, so that might be big enough. I'm not using the speech because I want you to have the fun of doing that on your own. But
I haven't gotten that far yet,
okay.
so.
What we're doing is it passes through this block. It adds bit errors get accrued. So now it's taking longer to get through. It's still running right now. It's done. And it's the reason why it's taking so long is because I'm putting in very high quality, 16 bits per sample. So there's very low quantization noise. And now save it to a WAV file, and then I should be able to listen to it.
The little tales they tell are false. The door was barred, locked and bolted as well.
So you hear that popping sound in there. Those are the bit errors that are occurring. And when we put in our Viterbi, it's going to clean that up. Or if I do the Viterbi scenario, which would be dropping that down to 6, just 2 dB signal to noise ratio difference in the channel, it's a waterfall shaped curve, as I talk about in the handout things roll off really rapidly.
The little tales they tell are false.
So it deteriorates pretty rapidly by just changing 2 dB in the channel. So you want to have good forward error correction coding to keep that from happening. At this point, I feel like I don't want to take any more time because we're well past the normal stopping point. But just read and do, and there's very few glitches along the way. I've pointed out one of the major ones, or a couple of them. Don't ignore the scaling factor, and make sure you trim the vector lengths properly so that you don't have a difference problem. Then there are a few other things that will come along that I've kind of pointed out when you get into part 2. But part 2, I think, actually goes faster than part 1. So there's really not a whole lot to do. It's just a lot of tutorial and a lot of kind of leading you into it. And then you get the hands-on experience. So I know Chris wants to continue the discussion we had on Slack earlier. He's maybe going to screen share something with me. I don't know. My plan right now, though, is I'm going to stop the video. So I'm going to go ahead and do that.